Chapter 7, Probability and Samples, the Distribution of Sample Means, Part 5. We ended chapters 5 and 6 with a demonstration of how inferential statistics are used to help interpret the results of a research study. In fact, we were presented with a hypothesis. A researcher was interested in the effects on growth due to a growth hormone. So we could hypothesize, or the researcher would hypothesize, that the growth hormone has an effect on growth. The null hypothesis, which is the hypothesis we're going to test, would negate that and indicate that the growth hormone does not have an effect on growth. In order to provide support that the growth hormone does have an effect on growth, the sample mean would have to be significantly different from the population mean. And we were given information about the population that's denoted here. So the distribution of the growth of rats was normal. The average weight was 400 grams, and the standard deviation was 20 grams. And then the researcher selected a sample of 25 rats. And those rats were given the growth hormone. They were exposed to the treatment. And we then obtained a sample mean for those who received treatment. Now again, in order for us to reject the null hypothesis, which is the goal when conducting a hypothesis test, we state our research, which is grounded in our interest, and the null hypothesis is going to negate that and say that nothing's happening. And that's the hypothesis we want to test, and that's the one we want to reject. We hope to reject this idea that the growth hormone does not have an effect. And again, the ability to determine if it has effect is grounded in how different that sample mean is from the population mean. If we were to construct a distribution of sample means using this population, the mean of means would equal mu and also be 400. And then we'll calculate the standard error of the mean in relation to this example based on the sample size, and talk about the shape. So first, again, we're using a sample equal to 25. So the standard error of the mean given distribution of sample means would equal the standard deviation of the population over the square root of n. The standard deviation of the original population was 20. We're using a sample size of 25. So the standard error of the mean is equal to 20 over 5. And that gives us a standard error of the distribution of sample means equal to 4. And we would expect the distribution of sample means to be normal simply because the distribution of the original population distribution was said to be normal. Okay, so again, we're talking about those characteristics, important characteristics of a distribution of the sample mean. The expected value of m, which is also equivalent to the mean of means and will always equal the population mean. The shape of the distribution is normal, even though n is not greater than 30. The original population was normal, the distribution was normal, therefore the distribution of sample means will be normal even though n is only equal to 25. And then the expected difference between m and mu is expressed by the standard error. So we'd expect 4-point difference between the mean of 400 and any sample that's collected with a size of 25, so 25 rats that do not receive treatment. So again, if I randomly select 25 rats from the population and calculate the average size in grams, the majority of sample means will be congregated around the value of 400 grams. plus or minus 4 standard error units above and below that value. That's where the majority of scores, or excuse me, sample means would reside. So the goal of this research or study is to evaluate the effectiveness of the treatment being the administration of the growth hormone. In the previous two chapters, however, we were limited to using a sample size of n is equal to 1 individual or one score. Now we can use any sample size, and in this particular case, we have selected n to equal 25. The researcher makes a decision about the effect of the treatment by comparing the treated sample, M, to the original population, mu. If the scores in the sample are noticeably different, again, collectively, when computing the sample mean is noticeably different from the scores in the population, collectively denoted by mu, then the researcher has evidence that the treatment has an effect. Our challenge is to determine exactly how much of a difference is necessary for us to say that the sample is noticeably different, providing support that the growth hormone does have an effect on growth. The distribution of sample means and the standard error can help the researcher make this decision. In particular, the distribution of sample means can be used to show exactly what would be expected for samples that do not receive any treatment. Again, the standard error is establishing this common region centered around the population mean. And those that do not receive treatment would be expected to congregate around the center. Right? We would expect the majority of sample means to fall within that region. This allows the research to make a simple comparison between the treated sample from the research study and compare it to the untreated samples from the distribution of sample means. If our treated sample is noticeably different from the untreated samples, then we have evidence and support that the treatment has an effect. In particular, in this case, that the growth hormone does have an effect. On the other hand, if our treated sample still looks like the untreated samples, then we must conclude that the treatment does not appear to have any effect. In other words, the growth hormone did not have an impact on growth when measured in these rats. We begin with the original population, as we just noted, and consider the distribution of sample means. And by doing so, we recognize the characteristics of the distribution of sample mean, which include the expected value of M, the shape of the distribution, and the average difference between sample mean and the population mean. And to review, the distribution of sample means is normal simply because the original population distribution was normal. It has an expected value of M that equals 400 because mu is equal to 400. And the standard error is equal to 4 because we take, to calculate the standard error, we took the standard deviation of the population, which was 20, and divided it by the square root of n. The n was equal to 25, so 20 divided by 5, and that gave us 4. So the distribution of sample means is shown here in figure 7.12, the untreated sample means. And notice that the untreated sample size of 25 should have a mean around 400. Again, this is what we would expect. We don't expect it to equal 400, but we expect it to be close to it. To be more precise, we can use these scores to determine the middle 95% of all possible samples. And you may be asking, where did this 95% come from? Well, we'll learn in Chapter 8 that we, as researchers, identify what we call alpha levels. It is the probability of something occurring, and they're an established percentage or probability that researchers have agreed upon that help us determine statistical significance. An alpha level of 5 is very common, as is an alpha level of 1. Essentially, we're as researchers saying we expect that something rare has less than a 5% chance of occurring, or less than a 1% chance of occurring. So we're setting the boundaries of what we would consider to be noticeably different. So if we establish this boundary, let's say 95% in the center. What we're going to do is identify what the grams in terms of weight would equate to this range. So we want to know what the sample average would equal on the low end and on the high end. We see that they've already been calculated here, but we're going to figure out how they came up with these values that establish the middle 95%. And what they help us understand is that if our sample of treated rats, if their growth is beyond those values, whether it decreases growth or increases growth, that we would then consider values outside of that range to be considered noticeably different. And again, allowing us to provide support for the hypothesis that said that growth hormone would have an effect on growth. Now notice something, a little preview of what we're going to talk about in chapter 8 is directional, non-directional hypothesis. So in this case, I just said that the growth hormone would have an effect on growth, which implies that it could decrease growth. Now our understanding of a growth hormone is usually that it increases growth. But even if it decreased it and fell on the left side of the distribution, we would still have support for the hypothesis that said it would have an effect. Had we specified the research hypothesis to state the growth hormone will increase growth, then we would focus on the upper tail, the tail on the right, and we would only get to reject the null hypothesis if our values were beyond the established region for 95% below a certain value. In other words, the top 5% occurring sample mean values. So we'll talk more about that in chapter 8, but I just wanted to introduce that idea of a non-directional hypothesis because we are concentrating on both tails of the distribution. So in order to calculate what these sample means would equal, we use our equation m is equal to mu plus the standard error of the mean plus, multiplied by our z-score. So we need to find those z-scores. Yes, they are already denoted here in the slide, but we'll find out how we came up with those values. And we have walked through an example like this before, but it's, again, a good review of how we obtain this value to understand the middle, most highly occurring sample means in a distribution of sample means. So if we replace variables, if we're solving for the lower end, our equation would be m is equal to 400 plus our standard error, which was equal to 4, multiplied by the z-score. And we're going to find out what that z is equal to. And it's going to be negative because we're working on the left side of the distribution. Over here, our equation would be m is equal to 400 plus the standard error, which is 4 multiplied by our positive z-score. And again, how do we find those z-scores? Well, we consider the middle 95% of the distribution. We recognize that that's not one of the columns in the unit normal table. But if we take 95 and divide it by 2, well, first, let's consider this. We take 95% and divide by 100 to get a proportion of 0.9500. And then, and the reason I converted it to proportion because our unit normal table is full of proportions, not percentages. And then if we take 0.9500 divide by 2, we get 0.4750. So if we split this in half, we would have a proportion of scores below the mean, and that proportion would equal 0.4750 or 47.50%, and the mirror image above the mean. And we've done this before, but again, what I'm going to do is use the area between the mean and the z to find what that z-score is in the unit normal table. So to save a little time here, again, I transferred the values. I had the middle 95%. I took half of that and came up with a proportion of 0.4750. I entered column D, which is representative of the area or proportion between the mean and the z. I found that value down here at 0.4750, and therefore I report the z-score is equal to positive negative 1.96. Again, positive negative because I have two values, one above the mean and one below the mean. Okay, so now we've identified the z-value that frames the middle 95% of the distribution. So the z-score is positive negative 1.96, and so we enter that into our equation. So the sample mean below the mean of 400, that sets the lower end of this range, would be 400, and the product of 4 multiplied by negative 1.96 would be negative 7.84. So essentially we're taking 400 and subtracting 7.84. So our sample mean would be equal to 392.16, and that's what we have here. And that's how we came up with that lower end of the range. And then on the right side, it'd be 400 plus 7.84, and we get a sample mean equal to 407.84, which is what we had already expressed and shown on this slide. So what we're saying is 95% of the time that if you take a sample of 25 untreated rats, their weight will range from 392.16 grams to 407.84 grams. 95% of the time, a sample of 25 untreated rats will range in that span of scores in terms of grams. Therefore, if we have a sample mean that falls outside, either on the high end or on the low end, then we recognize that that sample mean would be rarely occurring, would be significantly different, noticeably different, and we would have reason to believe that it was due to the hormone. The hormone produced these a sample mean outside of this range. So for example, if I took a sample of 25 rats, I exposed them to treatment, and after receiving treatment in a period of time, I took the average of their weight. So I selected 25 individuals. I take all of their individual weights, take the summation and divide by the 25 I have. And let's say, for example, I had a sample average equal to 390 grams. Where does that fall on this graph? Well, it would be to the left of this value here. So 390 would be somewhere over here, and it would fall in the region that is not commonly occurring. Again, 95% of the weights for untreated rats will fall within this range, and this sample mean of 390 is outside of that range. So that gives us support to say that the growth hormone had an effect on the growth of these 25 rats that received treatment. Similarly, if we had a sample of 25 rats, they were exposed to the treatment, and after treatment, their average was equal to 415 grams. Where is that on this graph? Well, it would be, again, in that uncommon region, and we would say that the likelihood of selecting 25 untreated rats that they would have an average weight of 415 is very unlikely and has less than a 5% chance of occurring. So again, it's always referencing back to the untreated population or untreated samples that make up the distribution of sample means. So in either situation, we would have data to reject the null hypothesis. Again, the null said the growth hormone does not have an effect on growth. And if we were showing that these values are outside of that common region, the established percentage of 95%, then we would reject that idea, the idea that does not have an effect, and we would have support for the research hypothesis that says the growth hormone does have an effect on growth, demonstrated by the probability of obtaining these sample means if we selected 25 rats that did not receive treatment. And this is a wonderful example to move into chapter 8, which is all about hypothesis testing. And this is what we will be engaging in. We'll be given research scenarios, and we'll be asked to identify the research and null hypothesis, which is which requires us to have an understanding of the independent and dependent variable. Again, in this case, the growth hormone is the independent variable, and the growth that's measured is the dependent variable. So you have to have a basic understanding of those concepts to verbalize and structure a valid research and null hypothesis. And then given the data that's collected and the parameters set by our alpha that we'll talk more about in the next chapter, we will then be able to determine if we are lucky to reject the null or if we fail to reject the null. So those are our options. We reject the null, which is the ideal outcome, or we fail to reject the null. So to fall into the second category of failing to reject the null, let's say again we took a sample of 25 rats. We exposed them to treatment, and after treatment their sample mean was equal to 405. Where does that reside? Well, it would be somewhere in here, and very close to the population mean. And in that case, we would fail to reject the null because this sample mean of 405 that came from the treated group is not noticeably different from the untreated population mean. So again, for these values, we would get to reject the null. Here we would fail to reject the null. And here we would get to reject the null. And again, the reason is that the sample mean of 390 and the sample mean of 415 are noticeably different. Statistically speaking, they have a very low probability of occurring if we were talking about 25 untreated rats. The sample mean of 405 is very common and centers around the population mean, so it's not noticeably different. So we would fail to reject the idea that the growth hormone does not have an effect. And I know it's a little confusing, the phrasing is confusing, but you will get used to it. In your notes, I would suggest fail to reject is similar to saying you accept. And the reasons, there are very specific reasons as to why we would not use that phrasing, that terminology. But if it helps you distinguish between the two, by all means, use whatever hints that you need to differentiate between this idea of rejecting the null and failing to reject the null. And so we'll end this chapter with a learning check. A random sample of 16 scores is obtained from a population with a mu equal to 50 and a standard deviation equal to 16. If the sample mean is equal to 58, the z-score corresponding to that sample mean is equal to what? So our equation is m minus mu divided by standard error. And if we replace variables, z is equal to 58 minus 50, and then divide by standard error. Now, this is a common mistake that many students make. They will report this, but that's in relation to converting an x value to a z-score. We're converting a sample mean to a z-score. So we have to calculate our standard error, which is the standard deviation over the square root of n. Standard error is equal to 16 over the square root of 16, our sample size. So our standard error of the mean is equal to 16 divided by 4, and we get standard error equal to 4. So now we can replace that variable. So z is equal to 58 minus 50 is 8, divide by 4, and we get a z-score equal to 2. So again, don't forget to do this. And please note that in the exam setting, we're going to be covering chapters 5 through 8. So you will be calculating z-scores for x values at the same time that you'll be converting m values into z-scores. So make sure that you pay attention as to what you're being asked to compute. In other words, if you're asked to compute a z-score for an x value, you don't need to calculate standard error, but if you're calculating the z-score for a sample mean, you must first calculate the standard error so that you can convert that sample mean value into a z value. In short, just be conscientious of the words score versus sample mean. That'll make a big difference in the equations that you use. Okay, so determine if these following statements are true or false. A sample mean with a z-score equal to 3 is a fairly typical representative sample. Well, we've learned that the majority of scores are going to fall within one standard deviation unit, or standard error units, I should say, for this particular chapter. Approximately 70% of values are going to fall within that range. And if we go out 2 standard deviation units, we've read in our text -2, +2, that's going to capture or encompass approximately 95%. It's a little bit more than that. And then if we go out 3 standard deviation units, we capture approximately 99% of the distribution. But this idea that the majority of scores are within one standard error from the mean implies typical representative scores or sample means. Anything beyond 2 is considered extreme or unlikely or atypical or non-representative. So we would conclude that this statement is false, that a z-score of 3 is considered very unique, very extreme, and very dissimilar to the population mean. Going back to the example that we just talked about where we frame 95% in the center, that z-score was 1.96 positive negative. And at that point, we had good reason to reject the null if anything fell into the tails. And here we're saying 3 standard deviation units, so that's implying very unique scores and very extreme values. Next one, the mean of a sample is always equal to the population mean. And that is false. We expect the samples to be similar to the population mean because they're coming from the population, but we also anticipate some discrepancy, some sampling error to occur because we don't have all of the X values from the population represented in the sample. So we expect some discrepancies between the two, and it could be that a sample mean is equal to the population mean, but it's not going to be the majority of the cases. The majority of sample means will differ from the population mean. And that concludes the lecture for Chapter 7. Please, if you have questions regarding equations, any concepts, or terminology, please post it to the discussion board. These lectures are embedded within a discussion board. All you need to do is click on the TAC icon and post your question, comment, concern regarding material in this chapter. Sometimes you can just think of what is the most confusing thing, or I refer to as the muddiest point, and post that, and I can respond, and perhaps other students can reply to your post as well. But take advantage of that resource or that opportunity to engage with me after you watch these videos to reinforce the material that's been presented to you.